Okay, so we will start to talk about the real material of the food chemistry. And today we will talk about water. Water, we will talk maybe 2 or 3 sections, so we'll say water number 1. So let's talk about all the details of the water. Start from some basic stuff. So water molecular, H2O, this is everybody knows. And the H is molecular weight is 1. We say mass weight. So we have 2, and the oxygen is 16. So the mass weight of water is 18. That is everybody knows. The second thing is that the characteristics of the water, we call it odorless, tasteless, and we all say it's colorless. But regarding the color, some people will say there is a little bit blue hue, H-U-E, so a little bit like a blue color. You can imagine, like the water, the ocean water, when you reflect it to the light, the sunshine, you see a little bit of blue. And also we say it is transparent. So these are second things, the characteristics. Then we talk about a little bit of physics. And we know the boiling temperature of water, we always call it 100 degrees Celsius. But keep in mind that is at sea level. So we will talk about the elevation. So how high it is, the place related to the boiling temperature. And we also talk about density. And the density, we know it is 1 gram per cubic centimeter, or we say 1 gram per ml. But be careful, that is usually we say at 4 degrees Celsius. We also need to know at 0 degrees Celsius, it is a coexisting of water and ice. But related to the ice, we will talk very detailed on Thursday. So these are some basic information. Then number 4, we learned in the other classes, the water is very important for the biological function. So they say any of biological body, it's almost, we say, 70 to 80% of the components are water. And related to the food processing, we always talk some about the food processing water. So let's say we will talk about chlorine water. This is antimicrobials. We will talk about detail. And we also have like a produce processing water. Produce processing water, usually we talk about water quality. So we talk about the chemical, oxygen demand. We used to test how many organic matters are there. And we also testing NTU, which means how turbidity it is. And related to the poultry meat processing, we also talk about chilling water. So chilling water, the temperature control is very important. That is set up as a critical control limits for critical control points. And we also know the water is a very good solvent. And we always want every chemical, they can be easily dissolved in water. So for example, if we are preparing antibiotics, lots of the antibiotics, let's say nitric acids, or let's say tetracycline or even rifampicin, they cannot dissolve in the water. So we need to prepare the alcohol. But alcohol is also killing bacteria, so it makes the process difficult. How we want to make sure it's dissolved in the water? We make them as a sodium chloride formation. So that's a good solvent. And we also know there is a beverages. Let's say you can make a tea, you can make a juice, you can make a coffee. So these are the very common knowledge. Now, very quickly we could review for our bacteria or human being cell membrane system, we had a fluid mosaic model. So we had a protein intersected with phospholipids, and every phospholipids, we have two sections. This is a head, we call it hydrophilic. And we're using hydrophilic to express it is like water or water-like. And the tail is hydrophobic. So we say it's dislike water. These are the terminologies we should already know, and we're going to mention later on when we talk about lipid section. So that's the first part, is all these basic information for the water. Then, that's number one. The second one, we want to talk about the chemical structure. So the chemical structure we mentioned very briefly, but here we can talk a little detail. It's very straightforward and very simple. We had O, then we had H, and H. Okay, so let's just draw another one right here. We have O, we had an H. Let's say we have O, and we have H right here, and H right here, because H2O. So first of all, we need to know, this is we call a covalent bond between oxygen and proton. And this is covalent bonds is very special, we call it sigma bonds. So we here mention sigma negative, and this is sigma positive, sigma positive. Covalent bonds, it is a very strong bond. So how many energy we need to break down? It is 110 kJ per mole to break down. We also going to talk about some other things. Angle is 104.5 degree. We will talk later on much more detail about that. And then the distance between the proton and oxygen is 0.1 nanometer. It is actually 0.095 nanometer. Now let's go back to talk about the covalent bonds. The covalent bonds, why this is expressed as a sigma negative and a sigma positive? Because when we talk about this water, we have O, and they shared with oxygen. So that's H, that's H. And we also have these two, we call it a lone pair electron. Now, because we mentioned about the electron negativity, the electron negativity value of hydrogen is 2.1, and the electron negativity value of oxygen is 3.5. So the electron will be more attracted to oxygen compared to the hydrogen. So that's why we express as a sigma negative and sigma positive. Now we know two molecules of the water, they could be connected together. So let's just mark these. This is also 104.5 degree. And they can connect it with each other. So they connected with each other, has another bond. This is hydrogen bond. And the hydrogen bond, we mentioned, it is a very weak bond. Now how weak it is, if you want to break down, it is only need 5 kJ per mole could be break down compared to the covalent bonds need more than 100 kJ per mole. Now what's the distance between two molecules of the proton and the oxygen? It is about 0.18 nanometer. Okay, so this is a very basic thing. We talk about chemistry standpoint, so what it looks like. By the way, the long pair here, we also call this is Lewis structure. It's like this. Okay, now we want to say something we mentioned in the first class. How we call the structure like this? We call the water is sp3 hybridization and tetrahedral arrangement. Now then, we mentioned about the electron, arrangement of the electron outside of the cell system. So what is this one means? And we talk about, this is pointed about dot Linus Pauling in 1940s. And then won the Nobel Prize of Chemistry in 1952. So we want to mention about what is that, what that means. Because otherwise the textbook tells you sp3 hybridization, you may not understand what that means. Or you learned from chemistry a little bit, but you may forget about that. So we have to refresh about what that means. Here's something I want to say is that when Linus Pauling started to do the research about sp3 hybridization, he did not start with water. He started with a very easy chemical. The chemical is we talk about already is CH4. It's messy. So we need to go back to talk about this guy, how it is connected. So we had a C carbon is like this, and then you have a 4 proton, and then they connected with each other, so they share. Okay, so what it looks like, this is easy. We have H, 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 and H. Okay, that's simple. Then we want to talk about what's the sp3. This is go back to talk about the C, we talk about 12,6. So what is their sub-layer orbital looks like? So we're going to have to draw a couple boxes again. So we draw like this, then becomes 1s, 2s, and 2p. So we have a 6 there, so the electron of also 6. So we go up, down, up, down, up, and up. Okay, so that's become 1s2, 2s2, and 2p2. So we write is a horizontal, but when we explain, we need to put in a vertical. So how's the vertical? We go this way up. So we're gonna write 1s right here. So up, down. Then This is a layer, okay. The outer layer is 2, so that's 2s. With here, that's up, down. Then we have a 2p right here. Somehow right here, that's 2p. And we have up and down, up and up. Okay, now the energy level, we know this is from low to high. And it's very important, there is a concept we talk about in the first lecture. The outer layer, which is 2s and 2p, these electrons we call valence electrons, because they are easily to reacted with other atoms while forming chemical bonds. So what are the here comes is a proton. So here comes a proton. And the proton is very simple. 1, 0. And what it looks like, oh sorry, we say 1, 1. What it looks like is up. It's 1s. So what happened? These 2s, 2p electron and 1s, they could be connected. Then become rearranged. Now how they rearrange? Based on this structure. And they first of all, they using chromatographer, they find it looks like, I'll just draw like this. Here is H, here is H, and H. So we share. They using chromatographer, they find this angle is 109 degrees. So here's a question. If you based on simply say Pauli exclusion policy, that electron directly goes there. It never will happen, have this morphology comes out. They observe this one, then they can have to explain it. So, Linus Pauling proposed that they definitely have some hybridization happen, which means a rearranged. So how they rearrange? When they rearrange here, is like this. So these things, they rearrange like that. That's called sp3. S1 sublayer orbital p times 3. And then this guy goes in, this guy goes in, this guy goes here, and this guy also goes here. So they become like that. That is called sp3 hybridization. So that is his first results. Then he go ahead to do the water. So what the water gonna be looks like? Then we need to go back to see the oxygen. So what's the oxygen looks like? Oxygen is 16.8. So what's the Z sublayer orbital looks like? That will be 1s, 2s, 2p. So you have up, down, and then up, and then down. Okay, now the same thing. You do a rearrange from horizontal to vertical. This is low energy to high energy. This is the first one, is up, down is 1s. And the layer here is 2s, up and down. And then here you have up, down, up. This is 2p. So what happened? The same thing. these in the outer layer, which is at 2s and 2p, we call valence electron. And then these valence electrons will be easily to be combined with 1s, that is proton. So these will be combined. Then they combine have a hybridization. So what it looks like, that's obviously is straightforward. It's very simple. Up, down, up, down, up, up. Is that right? That's sp3, 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 sp3. And this guy goes in here, this guy goes in here. So you have, that's sp3 hybridization. Now, they go ahead to do the morphology observation. So I want to draw this picture a little bit better. So I always use this notes. So what the water looks like. Okay, here, it's oxygen. We have a little bit of like a flower here. Okay, here, like here. You have this guy comes out, this guy comes out, that comes out, that guy comes here. And when they comes here, they of course they have shared. The long pair is right here. Long pair is right here. Okay, that's H. That's H. Now what they find? They find this angle is 104.5. Now there is a question. You say the meson sp3 hybridization is 109 degree. How come here in the water you find 104.5? Now what's the difference? It's obviously later on he pointed out. Meson, they are equally shared. For the water, there is a lone pair electron. And then they push the angle from a little bit, from 109 to 104.5 degree. So this comes out the explanation of sp3 hybridization of electron subatomic arrangement of the water sample. And this alone gives you Nobel Prize in 1952 of chemistry. And this is very important. That's why I want to be sharing with you. Okay?
Dr. Shan, question. So 2s and 2p combine together with the hydrogen to make sp3 hybridization, right?
Yeah.
So what's the energy level of sp3 hybridization? Is it at 2s or 2p? Like, is it
It's rearranged. So S and the
Yeah.
P they combine.
Yeah, but what's the energy level? Where does it like fall in the energy level? Is it in between these two or?
When they are rearranged, this become a layer.
Yeah.
That's higher than that 1s.
Okay. So,
Yeah, that's
so
what it is.
close to 2s.
Yeah.
Okay.
Because if they don't do this, this will not happen. This is all the time they do the morphology, then they talk about structure. They have to be combined. You know what I'm
Yeah,
saying?
yeah.
Then they become the same energy level. You know, the same thing here. The only difference is this have a long pair, this doesn't have. That's why they push the angle a little bit.
Gotcha.
Yeah, that's a very interesting topic. So this is the sp3. Now, let's go back to very quickly review. What is sp2? That is interesting. So we skip all these, okay? We have 2s, and then we have 2p. So what is sp2? sp2 is very simple. It looks like that. So I shouldn't draw like this. I should just draw 3, which means these two combined. That's sp2. So what's going to be the angle looks like? That's very simple. 120 degree. Now that's SP2. Now what is SP from the chemistry? Let's still go back to talk about the 2S. So we go here, we talk about 2P, and then we go here, so you become, that's SP, which means these two, they combine. Okay, so what's the angle looks like?
180.
Yes, 180 degrees. That's very basic chemistry, but we go back to review it. Okay. Okay, so we finished talking about here. We're gonna talk about something for the water. Okay. Let's talk about something not in the textbook, but I think it is important. We will comparing several concepts. First thing, hot water versus soft water. Everybody knows what is hot water. If you get a pound of water, that is hot water. If you get our municipal drinking water, let's say just tap water, or just say tap water, it's ideal, it should be soft water. Although we know in the West Virginia and Pennsylvania, this area, you see a heavy amount of the calcium magnesium here. So that's something else, but ideally, municipal drink water is soft water. So how we differentiate that? So in the United States, we basically talk about calcium and the magnesium level. So the calcium level has to be 40 to 80 ppm, parts per million, and magnesium is 20 to 30 parts per million. How we know about that? We based on the different chemical formation. If it is composed about calcium carbonate, or it's composed by magnesium carbonate, they can be reacted with water and at a very high temperature. So we using boring methods. They will cause precipitation, become calcium hydroxide and magnesium hydroxide, and also release carbon dioxide, although we may not notice that. So this type of thing could use a simple methods, use boring methods. Using boring methods can solve it. We call these are temporary soft hot water. Temporary hot water. And if the components is like calcium chloride, magnesium chloride, and we also see sometimes calcium sulfuric or magnesium sulfuric, these, we using boring methods cannot solve the problem. This we call it's a permanent hot water. Although people will tell you they're using nanotechnology or like combined with filtration or something, they could break down them, but from the chemistry textbook standpoint, they still think these are permanent hot water. So that's temporary hot water. And temporary hot water, we could do the observation, which is everybody at home has a hot pot. If the hot pot, you do a boring all the time, you will see a couple months later, there is a very heavy precipitation at the bottom. That is possibly is a residue of magnesium and the calcium. Okay, so that's soft water and hard water. Now, something else I want to say is that United States municipal drink water is drinkable. That's related to another issue is microbiology. The EPA have a regulation is coliform and the fecal coliform that is zero tolerance. So that's why we're using like a 3M petrofilm, we can do the identification. Now that's microbiology, so we don't want to talk this one too much. The second thing we want to do the comparison is we call free water and or free available water versus bound water. Bound water usually mention about the monolayer, we will talk about that. So free water, everybody knows free water. They can be a very good solvent. They could be created through filters. So if you have, let's say, a meat products, you put it on a filter paper, and you're gonna see there some of the dripping comes out. Okay, that is free water. They also could do is a centrifuge. Everybody knows in the lab we have a centrifuge machine, and if we do a centrifuge, let's say a meat sample, if we do a centrifuge at like 4,000 G for 10 minutes, you will see all of the tissue at the bottom, and then the water comes out on the top, and that is a free water. Now, what is a bound water? The bound water have several things we want to say is, number one, this is one is not for solvent. That's obviously cannot dissolve something. Number two, this is not frozen, even at minus 20 degrees Celsius. But people have to be careful about that. You don't feel about bound water. But bound water is widely existing in the food products, even in a produce. Vegetables and fruits, there is about 8% is bound water. In the meat products, there is about 11% is bound water. And if you have egg mayonnaise, then 0.4 gram per gram protein, those are bound water. And it is important because it's a connection between the emulsification system. So that is a bound water. Now, we also want to say that there is a new methods. We could differentiate free water and bound water. We call it the nucleic resonance, magnetic resonance. Using these methods, we could differentiate free water and bound water. Now, this is a very simple concept. You even learned in your chemistry somehow in the high school. Okay, now next one, we want to talk. The key for the chemistry, the concept is important, is moisture content versus water activity. I just use AW because I'm assuming all of you know what activity is AW. Why I want to spend time talk about this one? Many years ago, in like 7 years ago, I have a graduate students. So I asked a question. I said, "What is water activity?" So she didn't even think. She just said, "It's a moisture. How much water in the food sample?" That is wrong because what she mentioned is obviously is moisture content. But I want to tell you the moisture content is even a little bit tricky. It's not that simple. Just say how many water. So let's talk about the moisture content. When we talk about moisture content in food chemistry, we add an E. That means equilibrium moisture content. Now, very simple to say is amount of water in foods or in food products. We just simply to say. But the calculation is a little bit tricky. So what happens is, let's say we have a food products. We know the food products could be simply separated into several parts. The easiest way we separate is we have a water section and a solid section. I'll use another. This solid section. And the total, we say, mass of moisture. So we know the water section and the solid section. Therefore, the moisture content, there are two different calculations. The first one is we call it dry base. What means dry base? Dry base means amount of water is a numerator. The denominator is the amount of solid. Of course, you're going to have to multiply by 100. That's called dry base. So in here, if you still confusing, we could draw is this section with this section. That's called dry base. The second one is most of the time we're referring to is wet base. So what is wet base? Wet base A equals amount of water divided by amount of water add, very good, add amount of solid. Multiple by 100%. Okay, so if you don't understand what this means, this is the amount of water right here. Then the next one is the housing. Okay, is the housing. Now, this wet base, if you want to make a little bit complicated, both of the numerator and denominator could be divided by amount of water. Okay, if you do the amount of water divided, that's mass, okay? This divided by amount of water. And this divided by amount of water. Then what is it equals? It is 1 divided by
1 plus
1 plus,
amount of solid by
yes, amount of dry base. Then the same thing, you can do the dry base. That equals, I believe, this equals 1 minus the wet base. I skip it, okay, otherwise you're going to have 5 minutes to talk about the mass. That's why I say the class needs to be a little bit of mass knowledge. I just skip it. What this tells us, tells us you don't feel weird if you see a textbook said or paper said the dry base is 400. It depends on products because that's a dry base. So lots of the time if you see a publication they say, moisture content of dry base is 400. You never understand. You see how come it's more than 400? Because of this mass. And the wet base basically is between 0 to 100%. So that's something I want to mention. Don't feel weird. Now, most of the time, so far, is a publication in our group. Dr. J, Dr. Martok, myself, we want to mention, we always refer to is a wet base. But you need to know the dry base. It's a little bit. The mass is right there. Okay? So that's the moisture content. Now, how to measure the moisture content? In our lab, it's easy. You have an oven. Set up more than, the oven you usually set up more than 105 degrees Celsius. Then you put in a tray, in a like a foil paper tray, you put food products. Is that right? Then you measuring the weight before and after, then you do the calculation. Okay? So that's moisture content. Okay, now water activity. What is water activity? I talk about water activity in the microbiology class also, so I wanted to re-mention. This is a very tricky, important concept. When you look at the textbook of microbiology, they will just say, this is available water for bacteria. I'll just say biological body to use. It is very simple. But the story behind it is a little bit complicated. What is water activity means? What is calculation? I will be draw this right in the middle. Okay, water activity. Water activity equals partial vapor pressure above a food product divided by partial vapor pressure, or we can just say vapor pressure above pure water. Now we also know this could be equilibrium relative humidity equals 100% multiplied by water activity. That's just the math. Okay, so what this means? This comes out with some explanation. We're going to have to talk. In a very simple closed vessel, it's just physics. So I have another closed vessel right here. So I put water there. Obviously, there is a water molecule. So I draw some. Draw 3. The water molecule will move in. Some of them will flee away of the water, go to the space area. And some of them will come back, will go back. Okay, it depends on the food products, depends on the temperature, depends on the volume, they're going to come back. At the end of the day, they will reach an equilibrium status. So what is the equilibrium status is, the water flee away. We call it evaporation. That equals condensation. Okay, therefore, above this intersection, there is a pressure comes out. This pressure called vapor pressure. And we said about the vapor pressure is affected by an important factor is temperature. If the temperature is increased, what will happen? The vapor pressure will increase because more water is evaporated. And then at one time, if the vapor pressure equals atmosphere pressure. What is the atmosphere pressure, the value? If you learn the physics at 1.013 multiplied by 10 to the power of 5 Pascal. What will happen? Very simple, that happen. We call it's boring. There's lots of people doesn't notice that. Okay, so let's say one standard P0, okay, atmosphere pressure buildup, like that. Now we know the partial vapor pressure and temperature, they follow a very important equation. Yes, Clausius and Clapeyron equation. What is that? That is a little complicated. We don't talk today. Okay, equals negative delta H, or and this is T or delta P. We talked this on Thursday. Okay. Very simple to explain this is there is a table. If the temperature is 40 degrees Celsius, this P is 75 torr, T-O-R-R. If this is 80 degrees Celsius, that is 55.5 torr. And if it's 100 degrees Celsius, that is 760 torr. That's a very old measurement of the pressure. 1 torr equals 133.3 Pascal. So that's a very simple explanation. So we don't want to talk about that. Now, this is the pure water. Let's say if we had the food products. We think about the food products is right here. In the food products, we of course we have lots of water there. Okay, we have water. But at the same time, we have lots of other ingredients. We have salt,